as I want to look at it with seismoacoustic data. And I want to use this time here on the title slide, of course, to thank the Vector Foundation for funding my research. Otherwise, this would not be possible and I wouldn't be here today. So let's get started with why it makes sense to use seismoacoustic data for meteoroid observation. And there are three main reasons why it makes sense to use seismoacoustic data. And the first one is that there are thousands of seismoacoustic stations around the globe. Here on the map on the right, you can see just Europe, and every white circle is a seismic station, and every red circle is an infrasonic station. So these data are all freely available, so everybody can get these if they want, of course. And these all can help close spatial observation gaps that we have with the commonly used meteoroid observation methods, of course. Secondly, we can also record all day and every day, so we don't rely on bad weather or the daytime, so we can even catch some rare daytime meteoroids if we are lucky, of course. So these seismoacoustic stations can also help close temporal observation gaps, which is really nice. And the third reason why using this kind of data makes sense is because acoustic waves produced by meteoroids, or any acoustic source in the atmosphere, travel very, very far. So we don't even have to have very dense networks, and we would still be able to record our signals, and we will still be able to reconstruct trajectories and other things. So what kind of signals can we expect from a meteoroid that we can measure at seismic or acoustic stations? And there are three main mechanisms in which a meteoroid can produce acoustic waves. The first one is the so-called Mach cone or Mach wave, which is produced by the supersonic flight of the meteoroid, which is an acoustic wave, of course, that travels down to Earth as more or less a planar wave. And when it touches the air-to-ground interface, it can also induce seismic waves that we can also measure at our seismic stations. The second mechanism is an explosion or fragmentation of the meteoroid, of course. Everybody knows this. This is an acoustic point source from which acoustic waves travel spherically. And these can, of course, also induce seismic waves when they touch the ground. And the third mechanism is an impact event where just the meteoroid hits Earth with very high velocities, and this just generates seismic waves directly. You should keep in mind the first two mechanisms because they will be important later again in the talk. So let's look at the event location. I know we already heard a lot about meteoroid BX1 tonight, but I want to touch up about this very briefly again. So it was January 21st at midnight of this year, and over northeastern Germany there was this meteoroid event. And this was, although it was seen by many, many eyewitnesses, only 37 reported these online. And these witness reports were, of course, aggregated by the International Meteor Organization, and they produced a trajectory from that. And I used this trajectory to more or less constrain my initial search area to this whole map extent you can see now. So I want to look at this whole map area at data. And first I want to look at infrasonic data, and more specifically infrasound arrays. And infrasound arrays are basically a multitude of many single observation stations that together form an array, so they are located very close together. And all of these triangles you can see in the map here are one of these arrays. So I got data from 9 infrasound arrays in this map extent. And the nice thing with arrays is that we can perform so-called beamforming techniques. Beamforming is essentially a form of stacking signals, so it improves our signal-to-noise ratio. So we can get signals from stations which are very far that would otherwise not get, or would otherwise be not able to recover the signals if they were single stations only. And the second nice thing about beamforming is that we can time track certain properties of our wave that travels over our array. And we can do this now, and I will show it here on the lower left, and I hope everybody can see. On the top is the waveform of this stacked beam, so it's stacked pressure, more or less. But more important is the bottom plot here, which we can use to actually time track the meteoroid. So we have on the bottom left the back azimuth over time information, which we can use to track the meteoroid flying from left to right here on this map. And we can, of course, do this for all our stations, and we can produce a nice confusing plot like this. You can see that we are missing 3 arrays on the top left or in the northwest. And this is because, most probably because of the wind, which allows or makes it hard for the waves to actually reach these arrays. Nevertheless, we can recover signals at arrays that are which the waves travel over an hour to, and this would, like I said in the beginning, not be possible for single station observations. And we use this now to a crossing of beams to find the most likely origin region for our signal, which is this red polygon here. Yeah, this is a nice preliminary solution, of course, but this is nowhere near accurate enough that we would want it. So we want to get closer to this. And we can only get closer by using a different kind of set of stations. So we now want to look at seismic stations, and you can immediately see that we have far, far more seismic stations than infrasonic stations. And all of these seismic stations can be used to reconstruct the trajectory from these single observation points. But we now want to concentrate our search area to this red polygon that we found in the previous step. So let's now look in this red rectangle where we can see seismic data more clearly. So here on the map on the right, you can see these seismic stations as triangles, and they are colored in respect to the arrival time. You can see in blue the trajectory from Pavel, and also you can see Berlin in green. And on the left, you can see the vertical components of our seismic stations. So these are the waveforms that we are actually measuring. And we identified the arrival signals at 17 seismic stations that I'm going to use here now. And we can recover signals in distances of over 200 kilometers and with time delays of over 650 seconds, which already tells us that this is a very, very slow wave, of course. And this is naturally the acoustic waves that our meteoroids is producing. So what we are going to do now is we are using these arrivals at the seismic stations to reconstruct a trajectory. And I did this with forwards modeling of acoustic waves that propagate through a realistic 3D Earth atmosphere with the software Infragar. And first I started with a simulation of a Mach source, which, like I said, is a line source along the trajectory. So along this trajectory, I simulated a lot of sources that produce, from there, with rays propagating down to Earth. And these intersection points where these rays hit Earth are now plotted here as these circles. And as you can see, these match. So we predict now arrivals, of course, with the circles, and we get measured arrivals with our triangles. So you can see that these match quite nicely, location-wise, the southern stations, but we have still a very hard time in the western part and also in the northeastern part of the map where we cannot really explain our arrivals at all in the moment. So what we did next is we devised an optimization scheme where we improved our trajectory guess every iteration to minimize our difference between arrival time predictions and measured arrival times, of course. And I want to jump ahead and show you the best fit trajectory that I got. And this is now here shown in green. And you can see that we can now resolve this mismatch in the northwestern part of the map, but we still have these unclear arrivals in the eastern part. And like I said in the beginning, there are two main mechanisms which are important for our where our waves are coming from. And first we have the Mach source, and second we want to also now include a fragmentation source. So I did exactly that, and also included fragmentation of the meteoroid, which now produces these nice circular patterns of arrivals around the end of the trajectory here. And now you can see that we can explain the eastern arrivals much, much better. And together we get a really robust solution for our trajectory, which yeah, is really nice. Next, I want to show you why we have to make it this complicated. In the easy case, you would just use arrival times and assume linear arrays and just do an inversion by arrival times. And I want to show you why this is not something we want to do here. And this is because of two reasons. First, we want to use a realistic 3D atmosphere velocity model, which leads to vertical bending of the rays, which you can see here. We have this nice bend. And this is, of course, far from straight anymore. And secondly, we also want to include wind into our modeling, which leads to horizontal bending of the rays, which you can see in the map here, for example, for this ray here. And both of these effects lie in the order of magnitude of 10 to 20% of our background velocity model. So these hugely impact our optimization. So if we wouldn't consider these effects, then our whole optimization would just break apart completely, and we would arrive at a false solution. And this is something we don't want, of course. So like I said, the green is our best fit trajectory that we got. And now I want to zoom in a little bit and look at how good it actually is. And I want to compare it with the optic solution, like you already saw in the talk before me. And the optic one is blue, the seismic one is green, and you can also see the strewn field that was shown previously, and the recovered meteorite mass is now colored from yellow to black, getting smaller in mass, of course. And while these both trajectories get apart a little bit in the end here, they are still relatively close together, actually. So they are around 5 kilometers at their tips apart. And from this, I wanted to also calculate a strewn field. And I just assumed that the last 10 kilometers of my seismic trajectory were meteorite generating. And from there, I simulated spherical and cubic fragments. So this you can now see here. On the top, you have spherical fragments, and on the bottom, the cubic fragments. And you can see we have a very nice match with the actual strewn field. So we can nicely match the ground truth of our locations with our modeling, which is really good and is a promising future for the seismoacoustic method. And with that, I already want to conclude. I don't want to spend too much time today. And I've shown that infrasound data here in this case study was not accurate enough. As you can see on the map here on the right, the acoustic gives us an area which is red, so really bad. And the seismic is, of course, very close to the optic one. Nevertheless, the infrasound method helped to pinpoint the greater area where we wanted to look at seismic data. And the driving point here is that seismic data is much more easily available, and we can get much more information out of that here. Last but not least, the main takeaway here is now that the seismic strewn field estimation and trajectory reconstruction is now in a state where it can actually help future meteorite recovery expeditions. And I hope you are excited for that, or excited as I am, at least. Thank you much for your attention, and I hope you have many questions.
Thank you, Dario. Again, impressive results. There's a question there.
Yes. Hello. Yeah. Thank you very much. I have a question regarding I'm very impressed how accurate that is. And my question is, would you be able to calculate that strewn field without having that bias? Right? Without having that bias from the strewn field calculated by Pavel, or without knowing the actual strewn field?
I actually plug no information in, so I just do it. Okay, so some information is, of course, in there, like density or some stuff, but actually it's more or less really free. So we are not really constrained to really background information, which is hopeful, but we'll see how good it actually is in the future.
Any other question?
How close were the radiants? I just see the projections here. So how close were the angles of the trajectory between the optical and
the angles? Yeah, the angles is the main big difference that I'm still trying to resolve why they are so different. They differ like I think 7 to 8 degrees, which is a lot. I hope I'm not saying something wrong now, but I can come back to you and give you the exact number if you want.
Yes, Nagatoshi?
Thank you. When you say the window effect, that means seasonally this effect changed that behavior.
Sorry, I don't think I really understood.
When you say the window effect,
yes.
Okay, so window effect maybe changes seasonally in winter season, in summer season. So my question is, your window effect changes window effect behavior seasonally or not?
I don't know yet.
So case by case would be?
I can just, I have to look at more events to really make an answer to that. Sorry.
Hi. How much have influenced density of acoustic and seismic stations relative to area for detect? Europe have a lot of stations, but Africa or Asia.
So to be realistic, you have to have like more than 6 stations in a radius of 150 kilometers around your trajectory. Then you might be able to reconstruct a trajectory. So this, I hope this gives you an idea. So if it won't work in Africa, of course. But for the infrasound data, it's more easy because we can get much larger distances. But then we also lose information because we are far away.
Maybe this question is not only for you, but all other speakers before. That did anyone try to investigate posteriori the meteorological radars? Because this could be also interesting to see. Now we have multiple channel data about this falling, and as far as I know, in America, this radar techniques is very, very effective for looking into the falling meteorite cloud. So did anyone, because I think from meteorological radar archives, it can be extract some data.
Yes, but not in Europe. The American ones are different. The European meteorological radar cannot.
Actually, could I make a comment on this? We thought about this, and in a different consortium, we had someone from the Netherlands who says he has good contacts to these European and German weather stations, and we wondered if we wouldn't be able to see something. And then he says the main problem and the main difference between the European, at least the German, and the US system is in Germany, they only keep the data for 2 days. And actually, in this case, we just had this meeting with him a week before this Ribberg fall, and I was one of those people informed very, very quickly by the ECHO. So, and we contacted him, and he gave him roughly the location around Ribberg, and he acquired quickly these data of all the neighboring stations, because within 2 days he already could do this. And he looked at it and says, no, he didn't see anything. It could be, of course, you have to be lucky. I think they rotate something every 20 minutes or so up to, I don't know exactly the numbers. You have to still be lucky, but in principle you could, but you have to be very fast in downloading the data. I think they don't keep them because it's so much data. So, but we gave it a try, and no, we didn't see anything.
Any other question?
So how automated is this sort of analysis? Do you have to do a lot of manual work to analyze all this data, try different approaches? Or have you written some code maybe that compiles all of this and might be shareable in some future?
In the future, it will be surely shareable, but now it's in a state it's like 50% you have to manually plug in, and 50% is now actually running. But this is all part of my PhD, so the end goal is, of course, that it will be running independently and fast. But of course, the future will tell, and I will tell you, of course.
Ritter?
We see that your trajectory is bent toward the real strewn field in the end. I mean, there in the lower right picture. Could it be that you actually recorded the meteorites in a dark flight, so below 20 kilometers? So by that time, they may have already started to be blown away towards the eastern direction? And could this be the reason why you have a different trajectory?
Recording meteoroids in dark flight with acoustic or seismic stations is not impossible, of course. But here in this case, I don't think so.
Okay. Thanks.
So there's an online question. The question is whether you did calculate the mass based on the seismoacoustic data, the initial mass.
Initial mass of the...
Whether you calculated that?
Yeah, for the mass of the fragments, I fortunately already knew the strewn field, and then I plugged in some numbers. And I don't know if I can go back. I can say that from left to right is 300 to half a gram. I was supposed to say that, but I forgot.
Okay, thanks. Any other questions?
What was the end height of your trajectory?
From my trajectory alone, it was 20.8 kilometers, but the last observation point was 26 kilometers high. So this is the full trajectory, but actually we get only information for points along the trajectory in which we reconstruct. So we don't know all the time points, of course, for the trajectory. We only know some of them. So in this case, 26 kilometers and not.
So how do you know that it's 20 kilometers if you don't have any data from 20?
That's just my assumption for where my trajectory ends, where I ended the modeling. So where this was the lowest height where I started the strewn field modeling.
Okay.
Thank you. Any final question? Let's check it again online. So I don't think so. So let's thank the speaker again.